Hello everyone. In this video, let's learn about three-state buffers. So first, what is a buffer? Gate output can only be connected to a limited number of other device inputs without degrading the performance of a digital system. So a simple buffer may be used to increase the driving capability of a gate output. So let's take this little example here. So let's assume we want to connect the output from this gate to several other inputs. So if we connect the output from this device directly to one of the inputs of the other devices, this may cause some degradation in the performance. Therefore, we can use a simple buffer to prevent this problem. We can connect it in this location. So now let's see the three-state buffer, or called the tri-state buffer as well. So a tri-state buffer represented as follows. So it has one input and one control input or enable input. So let's call this input A, and let's call the control input B, and then the output C. So this is equivalent to this representation here. So this is A, this is the control or enable input B, and this is the output C. So let's see what happens when B equal to 0. So when B equals 0, so that means this gate is open, so we have an open circuit. So that means C output is disconnected from the buffer output. So this is referred as high Z, stands for high impedance, because the circuit offers very high resistance or impedance to the flow of current. So what happened when B equal 1? So when B equal 1, so this gate here will be closed. So we have a closed circuit, and then the output C will be equal to A. If A is 1, C is 1. If A is 0, C is 0. So now let's see four kinds of three-state buffers, and along with their truth tables. So this one here, the one we just drew above. So we have input A, control input B, and then output C. We have another type. We see a little bubble here at the end. This is the inverter. So we have input A, enable input B, and then C. We have this kind here. So we have the bubble here on the control input. So this is B, this is A input, and this is C output. And also we have this kind of three-state buffer, which we have an inverter on both the control input B and the output C, and this was input A. So let's see the truth table for each one. So the truth table, we have two inputs A and B, and then we have output C. So for A-B combinations, there could be 0, 0, 0, 1, 1, 0, and 1, 1. Let me make 3 copies of this table here. And now let's fill these tables. So let's look at B. When B is 0, for this one, we have an open circuit, right? So we have high impedance at C output. So this is Z, and this is Z here, which corresponds to B equals 0, right? So next, let's see for 0, 1. So now B is 1, so the switch is closed, and then we have A is 0, so the output will be 0. And then at this last row, A is 1, so this will be transferred to the output 1. So next, let's see for this kind of tri-state buffer. So here we don't have a bubble on the B input, so that's the same idea. So when B is 0, we have an open circuit, high impedance. So when B is 0 in this row here, we have high impedance Z. And then when B is 0 in the third row, we have high impedance Z at the output. Now let's see when A is 0 and B is 1. So B is 1, the switch is closed. So A is 0, we have a little bubble here. So the output will be 1, the opposite of A. In this last row, when A is 1, the output will be 0. Now let's see for the third kind of tri-state buffer. Now we see the bubble here at the control input B. So that means when B is 1, we will have an open circuit, because after the bubble we will have 0, which means we have the switch is open. So when B is 1, in this row here we have high impedance, and then the last row we have high impedance. So next, when A is 0, we don't have a bubble here, so the output will be the same as A, will be 0. And then in the third row, when A is 1, the output will be 1. Now let's see for the last kind of tri-state buffer. We have bubble on the B input and we have bubble at the C output. So same idea, since we have a bubble at the B, so when B is 1, that means after the bubble we have 0, so we have an open circuit. So when B is 1, we have high impedance, which is in this area here. And then in this last row, B is 1, we have high impedance. So next, when A is 0, we have an inverter bubble at the C output. So that means C will be the opposite of A, which will be 1. And then in the third row, C output will be 1, it will be 0, the opposite of A. So next, let's see how we can create 2-to-1 MUX by connecting buffers together. So 2-to-1 MUX from buffers. So let's see what happens when we connect these two buffers together. So we have this one, we have a bubble on the control input. I'm going to draw it at the bottom. And then here we have one input, let's call it A. And then let's see, we have another tri-state buffer, no bubble, which is just connected to this control input. And let's call this one B. And let's call the input of the second buffer, let's call it C. And then the output comes from these two buffers, let's call it D. So this circuit here is equivalent to 2-to-1 MUX. So this input is A and C, and the control input is B, and then we have the output D. So let's see how. So when B is 0, so B is 0, so we have a bubble here, so this will be 1. So that means we are transferring A to the output D. So that means A is equal to D. So when B is 1, so we have a bubble here, so the output here will be 0. So we have an open circuit at the top buffer, and then here we have 1. So we are transferring C to the output D. So in this case, D is equal to C. So this is the same as 2-to-1 MUX. So this will be 0, and then this will be 1. So this was a brief introduction to tri-state buffers. I hope this was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.